Let me put this to record. Did it start recording? Yeah, it looks like. Okay, so we have around 16 people. Let's get started. So first, welcome everybody to this special presentation we have today. We're gonna have Hector Lopez presenting about WMDs for the information age. I looked at EMPs and the vulnerability of our grid. This is something that is an interesting presentation. I looked at it. It looks pretty good. It's lengthy and technical, and hopefully a lot of you have questions. I certainly have a lot of them. We're gonna reserve the questions for the end. This is something that was new to me, and quite frankly, it was something that I started researching because of chatter, right? I started getting pinged by people, uh, all kinds of channels about this, that if I knew or if I heard. Um, so at first, I sort of said, I dismiss it. But then it became a little more noisy, and then I started to worry about it. And once I started to worry about it, that's when I started reaching out to people. So here's some of um, the things that I would like to do. I'm gonna put these things out there. This doesn't mean that I know something classified or know something that you don't know or you should know. These are things that have been happening, and there's been chatter about this now for some years. And as you can see, some of these items are actually pretty recent. Does this mean there's something going on? I don't know. I'm a civilian. I don't have access to classify information. I do get pinged sometimes by people that know, and that's usually when I worry. Um, and here's some of the headlines that uh, have been coming up. There's no really anything particular about these headlines. I chose them because I wanted you to see that there's been a timeline where this subject has been brought up. We all know what's going on with the pandemic. There's also several geopolitical theaters where there's a lot of tension. And then, we've been having this chatter about this. So, are all these coincidences? There might be. Is there something going on that we don't know? I had no idea. But if there was, then we had to make an effort to prepare, and we had to make an effort to understand what we're facing. And that's why I recruited Hector, and I have other people here that have worked with this as well, and I'm sure they're going to chime in as we go. So here's some of the chatter that's been going on, and I'm going to show you three things that I wasn't able to put together until I started seeing the chatter. So um, I always wonder what had happened at this station in Silicon Valley. Then I come to find out that this was actually a sniper attack against an actual substation that feeds Silicon Valley. And if they had been successful, they probably would have caused a lot of damage and would have left a lot of people without power in one of our main economic and technological centers. This happened in 2013, and it actually happened again sometime after. I had talked to some people in California, and if there's anybody watching this presentation from PG&E, we're more than welcome to have you speak. We're more than welcome to tell us the California side of these events and preparedness. I know you guys are probably, your hands are full with all the fires and all what's going on, but this is a significant event that happened in 2013, and it was a bunch of people that were dressed up, cut off the actual video line for surveillance in this station, and then they shot at the transformers with AK-47s. They really weren't successful, but this is something that was notable. And then this Metcalf station, which is actually very important in Silicon Valley was vandalized again and was attacked. So there's some questions about what this event, what was behind this event, and this is what I would qualify as a sabotage or as an internal attack in the grid. Then this is another event that happened in 2017, and this is a gentleman whose book inspired me basically to do this, to try to gather all of you for this presentation. Is Dr. Peter Pry, who is an expert on this, and he was recently on TV explaining all the possible attack vectors that had to do with the blackouts and with the vulnerability of the grid. And he's got a book which is called Blackout Wars, which I highly recommend you read. And I'm sure Hector or somebody here that knows about this will touch on this book. In this case, and this is something that I'm putting out there so you understand. I personally didn't know about this. I went to a person that is very close to me that has worked with satellites and rockets and asked this person, is this possible? And the answer was yes. There is a way to use satellites that could appear to be for something that is not military and carry a payload that can produce, for example, an EMP. And I saw the slides, and this is going to be covered during this presentation, but this just happened. The country specifically is North Korea. The specific satellites, the KMS-3, and this happened in 2017. And finally, before I pass it to Hector, the threats about against the grid is not only man-made. We can have a natural event, and this has happened before in 1859, where there was what is called a Carrington event, and apparently this was incredibly harmful to whatever infrastructure was at the time. And there is some data that indicate that this may happen again. And I actually went again to a person that I know has worked in a government agency that has to do with rockets and satellites and you name it, and the answer was yes. There's a good chance that this will happen again. So these are things that should drive us to prepare for this. Why? Because most of us here are in cybersecurity. And there was one thing that I picked up from that book. He said that the EMP, the whole EMP area should be covered under cyber, because if they fry the whatever it is either by an attack man-made or by a natural occurrence, there won't be internet. If there's no internet, and we are all fried pretty much. So with that in mind, I actually went into ready.gov, which is usually what most of us look at when hurricanes are coming, and come to find out there is actually a space weather preparation. So you can check this out as well, because I'm sure many people would say, okay, what do I do? We will get into this in a minute. And with this in mind, I'm going to pass it to Hector, and hope all of you guys bring in some good questions. If you have something that you want to chime in and comment, let Hector do his presentation, and then at the end we can all talk about it, and let's take it from here. All right, Hector.
All right, let me see if I can share my screen. All right, good afternoon, guys. Again, like Rod said, this topic is interesting. I started researching this topic. At first, I thought it was pretty simple. So I have an electrical engineering background, and when you're introduced to these EMPs, it's kind of very sci-fi-ish first, and then you start seeing, oh, it's just a little, like, a little effect that happens when you're working on some electrical equipment. But what he was talking about with the blackout wars, it did open up a Pandora's box, and I started researching into the references that I had, mainly from the government references, and I found a lot of interesting things. So that's why I named this topic like weapons of mass destruction for the information age, because they can be, it's a new way of starting warfare against other countries and affecting the information age, which is our internet, which is our communications, and it's a new way of cyber threats, a new type of cyber warfare. And one of the major things that can affect that is the grid, or can be affected by that is our grid, is our infrastructure. So let me just start out with my outline. So I'm going to go over a disclaimer and talk about a little bit myself, and then I'm going to have it into two parts. The first part is very basic. I'm going to talk about electromagnetism. So I really want to touch on this so that you guys can appreciate the latter section, which is more of an overview of the things that Rod is talking about, the threats, the mitigation steps, and what is the state of our grid and our infrastructure today. And then I'll go over a summary and acknowledgements and some questions at the end. So I have to say this part because I do work for Fluid Power and Light Energy Services. It's a subsidiary of Fluid Power and Light and NextEra Energy. I do not represent them in this talk in any way, shape, or form. All the reference material is publicly available. You guys have access to the same reference material. Any expressions of ideas, opinions that I express in this talk are my own, not of my employers. Okay. So my background real quick. I joined HackMiami about 4 years ago. I came to some of the CTF tournaments and in the Fort Lauderdale Museum of Discovery area, and it was a lot of fun. I enjoyed the people, the learning, the education that I got there, and so ever since then I've been kind of I stayed in the Slack channel, just watching you guys provide threat intel, and it's helped me in my career understanding the threats that I could be facing, and every time I would see a new threat come in, and you guys kind of talk about it and explain some of the details, the technical details around it, it helps me to build better systems and to kind of engage with my cybersecurity team and my IT team and my engineering teams and kind of build systems that are reactive and resilient towards those types of attacks. I have an engineering background, and I just love these types of topics. I also do a lot of software development and a lot of focus in AI and how to apply AI to control systems and help things like renewable energy and the grid. All right, so part one, just the basics. And the basics, we have to start out with electricity, positive, negative charges, all those charges. Particles are charged particles, and they have these attraction and repulsion forces. And once you start moving those charged particles, like let's say they want to attract or they want to move in some direction, they create a magnetic field, which also has an attraction and repulsion. And this is the basics of how we can create motors with permanent magnets and have electricity come out of those motors. You could have electricity into a rod, and they can move and have induction and actually create electromagnetic forces. So why do we have to start there? I really wanted to start there so you guys can understand that we build around this effect. We build around this phenomenon. So there's the reason why we have twisted pair is so that we could actually counteract some magnetic fields in the twisted pair and create more shielded signals in our electrical line. So that's why the twisted pair is one of the standards for cabling. We have coaxial cables, for example, that have that shielding and that insulation as well to kind of protect it from noises and outside interaction. So electromagnetic waves, electromagnetic interference, electromagnetic forces all start from this phenomenon of electromagnetism. And we build around that. So real quick to understand the electromagnetic component of this whole EMP thing, I really want to stay a little bit around the electromagnetism, how it's generated. If you have some current through a conductor or wire, you'll create electricity in one, electric force in one direction, and in perpendicular to that, you'll see a magnetic field around that. And so this illustration is really intuitive, I think. If you have some current going through a wire, you'll have a magnetic field around that. And then what ends up happening is because electromagnetism, electricity and magnetism is kind of like a interlocking force, you see these changes in the field. So the magnetic field will turn in this direction as electricity flows through a current, flows through a conductor, And then you have an electric field that will be generated from the magnetic field, and then a magnetic field from the electric field, and so on and so on and so on. So this movement of fields is what you start seeing looks like a lot like a wave. And we could create these fields, and these fields can basically work on each other. And what we'll talk about is this electromagnetic wave can induce current on a conductor, and that current can also generate the electromagnetic wave. There's a reciprocity feature there. Also, these things can be known as like radio waves. Radio waves, you guys are familiar with radio waves. This is how we generate signals off an antenna. We really just kind of oscillate current through a wire, and you could even, if the antenna has a point, energy will follow that point. These waves kind of emanate from these wires. So we could create signals from these electromagnetic waves. Some properties of the wave that are going to be important is frequency. And frequency is just a measure, basically it's a measure of the wavelength, the peaks between, the distance between the peaks of the wave. So the wavelength between these peaks is a measured in distance. And the closer that is, smaller the wavelength, the higher frequency is the signal. And I'd like to mention here that as you see the magnetic field and the electric field kind of like what do you call it? Like a seesaw type pattern where they kind of interact with each other. They're constrained by that interaction. And as the current flows in one direction, you have these fields kind of feeding off each other, bouncing back and forth in a perpendicular way, 90 degrees from each other. And we can measure the frequency of this wave. And as the wave, if the wave is very low frequency, right, it can be like the size of a football field. Like radio waves are really large waves. And then they could even extend all the way to gamma waves, which are really, really high frequency, very short wavelengths. Interesting enough, everything under this visible light wave, which you guys are aware that light is also an electromagnetic wave that has the electromagnetic properties of it. But it's very different because anything above this visible light, light is actually at the edge of the frequency that can have an EM wave that actually matters, that induces currents in material. And that has to do with some other properties of physics, like plasma. The plasma frequency of certain materials has to be proportional to the wavelength of that frequency. So basically what we're talking about is like anything that is not light, like the low light, you'll have the effects into materials such as conductive materials like metals and things like that. So that's why you can't really, you can have fiber optic cables with light passing through it, and it doesn't really get affected by a moving magnet or some sort of generator next to it. So that's just a caveat. I won't go too deep into the physics. If you guys want to look into that, you can look at it in your spare time. But we're going to be looking mainly at these frequencies below visible light. And this is where this EM field really affects things like EMI, other devices and machinery that we're going to be talking about. And going into EMI, it's a term for electromagnetic interference. So we look at any type of power source that is generating these electromagnetic waves, this movement of electricity. You'll have these things emit this radiation of EM fields. And these fields will have these wave-like properties, and these things are passing through us all the time, all over the place, because we have power lines and transformers and devices in our homes that are just emitting these things. For the most part, they're harmless. You have waves passing through you all the time that are very low energy. They're not really doing much. When you have lightning, for example, lightning actually can emit these waves in all kinds of erratic areas. And when these things are just being emitted and they're just kind of floating in space, you're going to have interference and interactions with other devices. These things are going to, it's going to be hard to filter out some signal, like from your radio blasting music, or than something that's, just creating noise. And similarly, you would have the same effects when you have devices trying to figure out what your radio frequency is with some music on it versus all this noise being generated by lightning, causing other frequencies and other things around that same space kind of interacting with that, that radio signal. So that's what we'll call EMI. Again, why is it important? all of our devices kind of, when we talk about telecommunications, use radio frequencies to communicate, some frequency range to communicate on. And this is mainly controlled by the FCC. They kind of create different bands and they say, hey, look, if you want to communicate low frequency here, and this is going to be like, you know, this particular band from 20 to 100, and you can do radio in hertz, or you can have higher energy like 4G and Wi-Fi. They can communicate in the gigahertz range. So these devices all use this method to communicate. And if you have EMI, you have these power sources just creating this noise, they can interfere with the communication of these devices. And that's on the telecommunication side. Also, if you have this noise and if it's strong enough, it could actually induce currents in these smaller devices. It could create these induced currents in these components that can cause damage. It could cause interaction. It could cause like bits to flip or communication to go haywire. So what we do a lot is we design these devices with circuitry to prevent or be immune to EMI. We also have the FCC, and there's EMI labs that will stamp your device before it goes out, like a radio-controlled car, for example, has to be able to emit in its frequency and nothing else, so it doesn't become a hazard to other things. So there's ways to control devices to emit the frequencies you need it to emit, and ways to protect the devices from being susceptible to noises that are being emitted from other devices in the area. So another reason why that is important is because shielding is taken seriously by the military. We shield things because we don't want other devices, noise to interact with our equipment when we're in the middle of the field, for example. And if the military is trying to communicate something important, they want to make sure that they're not getting any interference. The other thing is you don't want anybody reading your emissions. Like if you want to communicate to somebody and you don't want them to know, or some third party to know that you're communicating to them something important, you don't want them to try to decipher what you're sending in an ancillary way through that EMI. One interesting example actually presented at a hacker conference in Europe was the idea of like being able to use the FM receiver of a cell phone that typically comes with radio receivers. The FM receiver is able to actually pick up the EMI off of the screen of an air-gapped computer. So eventually you could kind of look at that spectrum, learn about it, look at the signature of what's happening, and then reverse engineer that signature back into actual information about what's happening on the screen. So technically you can kind of like, you know, read the password off the screen that's air-gapped just through the EMI. There's a lot of really interesting research, mainly around, it's called Tempest, and that research stretches back to the 80s, where people have been able to use this EMI coming off computers, off of cables, off of computer systems from another building away, and be able to recreate, for example, the keystrokes off the keyboard or the video transmission off of a VGA cable that's not shielded. So that led the government to implement all kinds of shielding standards, ferrite chokes, and different types of red cables that are like specially lined just to protect them from that kind of thing. Electromagnetic pulse. So we've gotten away from electromagnetism. We drove all the way up to this electromagnetic pulse idea. And when you hear electromagnetic pulse, that word is kind of loaded. A pulse typically is kind of like some kind of square wave or something. In electrical engineering, you see the square wave made up of many different frequencies. But in reality, this amalgamation of tons of different frequencies together will get you the square wave. But in reality, what we're talking about when we talk about EMPs is just it's better modeled with this double exponential curve, which is a quick rise in energy, and then kind of like a little trough, or a little peak, and then a slow gradual decay. And that's what we talk about pulse. So you'll see a lot of material on EMPs, and we're talking about this kind of like a jump in energy and kind of like a tail off. And later on, I'm going to talk to you about the different components of this signature. So you'll see that rise is a particular component, how fast it rises in energy. And then the fall off, that tail, is also a different component that has a different type of effect to devices and infrastructure. So really quick, how to make a low power EMI, EMP kind of device. You can Google it, YouTube it, but it's technically possible. You'll need some type of like high voltage component, like you could get a ballast from a fluorescent light. You can get like a Polaroid camera. That Polaroid camera, when it starts charging up and throws off the flash, that's setting up that voltage in a capacitor. It's loading up a lot of energy. You could use, you could even use a bug zapper, has high voltage ballast in there. So these devices can be used to create kind of like a taser. And that taser effect, instead of just having it spark through 2 leads, you take that really kind of similar to having like a rock off the Empire State Building. And as it's falling, you want it to go through coil. Electrons, as they fall, they want to go through, you put them through a coil, and that coil actually creates that magnetic field. In a coil configuration, what ends up happening is you have a lot of these circular magnetic fields. Imagine this yellow conductor as a donut, and you have these coils kind of rolling around that donut. All of them pointing in the same direction creates this really strong magnetic field in one direction. What's cool about that is then you create this electromagnet basically out of a really high voltage electromagnet, and that pulsing energy can actually shut off phones. It could shut off, like, it could create like, it's kind of the same thing you would get when you kind of expose your laptop to a big magnet. You can kind of like either wipe your hard drive if you have one of those old disk drives, or it could just shut off your phone momentarily because it's basically stopping the flow of electrons with this higher magnetic field. But technically, for the most part, if you remove that field away from it, it'll just turn back on. If you have devices that are older and you expose them to these types of magnetic fields, you could cause some devices to create a little bit of current in the wrong direction that can end up either short circuiting things or breaking some diodes down, blowing some fuses. So it's possible to create damage if you did it right. But these little homemade devices are very interesting. So if you guys are interested in trying to test out EMI and EMP effects on your own without shocking yourselves, you could test that out. Again, this is very low powered compared to what we're going to be talking about next. So these little devices and things similar to this, you could protect against. You're talking about, things that simulate kind of like what a lightning radiation would do. You can protect against those types of things like electrostatic discharge bags, act like Faraday cages. You can create shielding and grounding that allows that current to flow through the surface of that conductor and not actually affect the devices inside of it. And that's technically what a Faraday cage is. And again, you can use fiber optics. Light is not affected by these effects. But eventually, when you put them into a conductor, then it would be affected. So sometimes you have to think about that when you use fiber optics. There's a device called EMP Shield, and this is something that Rod pointed out to me, and I looked into this device. And now, the caveat is, this EMP Shield does protect you from some kind of EMP effects, right? But it's if the EMP rise time is very low, like it's typically around 1/1000th of a second. If it's higher than 1/1000th of a second, this thing will shut off, protect your equipment from being damaged because it'll pick up that current. But reading the literature, most E1, or I haven't talked about this, but the rise component of that EMP is much smaller. It's in the nanoseconds, like 1 nanosecond. So your 100 nanosecond device is not going to be fast enough to protect you against a high-powered nuclear-based EMP attack. So that's the caveat I have for this device. But for all the other types of situations, you can use this device and pretty much can protect you. But the best way is to preemptively create a conductive cage around something. And that conductive cage will protect you from getting that energy to flow with whatever's inside of that cage. It'll go around the edge of it. The caveat for that is, when you create Faraday cages, which is just this, protective shielding, the frequency of what you're protecting against is important. So the wavelength is important. You can't have holes in that shield that are bigger than the wavelength of what you're protecting against. And unfortunately, really high-powered EMPs, they have such a wide range of frequencies that you're gonna, at the top end, you're gonna see, you can only build a Faraday cage that protects you from these really high energy EMPs that has 3 millimeter holes in it. That means like no gap greater than 3 millimeters has to be, it can be there. So you have like these welded edges, like in this example here, you have a lot of welded edges, you have a lot of very clean cuts, and that will be an effective shield versus for these higher energy EMPs. Okay, where do high power EMPs come from? Let me check my timer quickly there. Okay, these high powered EMPs that I'm going to be talking about next, they're different than the low powered ones, but they can occur and they can be man-made. So you could have, you know, equipment, apparently spark plugs, electric motors, they can create these effects, power line surges. Again, we're going to talk about nuclear, non-nuclear EMP weapons can create these effects. And then naturally occurring things like lightning, kind of like EMI-ish type stuff that creates, but at high energies, you can see the same similar effects, electrostatic, and then coronal mass ejections. These are the solar flares, the solar storms, that solar weather I was talking about. These things will come at the Earth, hit the ionosphere and magnetosphere, and create these effects on Earth. Okay, going there. So in summary, EM waves are coupled electric and magnetic fields. These EM waves can cause interference on some devices. Devices are susceptible to EMIs if you're not protected correctly. There's a lot of protection in these devices nowadays, and there's products out there that can help you protect against this basic EMI shielding, you know, EMP style attacks and things like that. Little devices are designed to create intentional EMI effects. The EMP is like a EMI that has large amounts of voltage and takes on a pulse-like shape. So it's kind of a more sophisticated than just random noise. High-powered EMP effects can be man-made or arise naturally, and we'll talk about that next. But that's cover the basics. And let me stop there and just take you know, a couple minutes for questions or any comments.
Yeah, so you mentioned on the Faraday cages portion of things. What are the limiting factors to something huge that you just showed, right, with all the welds? And let's say that, hey, I can't build something like that, but I want to be able to protect like a small rack server, right? Like
Yeah.
almost like the size of a nightstand type thing. So what would be the best way of either buying it or DIY?
Yeah, again, Faraday cages are pretty simple. You could make it out of aluminum foil. It just has to be a continuous surface. If you have a continuous surface with apertures that are small enough, so in this case, to protect against a high energy EMP, like a high altitude one, you're talking about 3 millimeters. But for other effects that are not as great, you could have larger openings. They sell those off. You could have like those mesh panels that they sell, I believe, in many places. They sell the aluminum meshes or aluminum holes in there. Depending on what you want to protect against, you can always use that. But as long as it's a continuous covering, if you build a box that covers your rack server with a continuous, you know, external shell, that's good enough. And then if you wanted to ground that external shell, you could do that too. You could take the a clip and you tie it to like a pipe or something that's wired to the ground, or stick a stick in the ground with a nail in it, and that's enough to basically create a shield with a grounding element on it. Did that answer your question?
Yes, thank you.
Hi, Hector. This is Ray. I had a question too. I just want to show we've kind of talked about it before. Because I've got a little bit of echo here. Maybe I need to kill my local speakers here for a minute. But you know, like here I've just got a metal can. I don't know if let me see if I can get it to show up in the picture here. Well, okay, maybe that shows up. And inside is a meter. One of those meters, and it's got a lid. Can you see it okay? You know, you kind of put sort of a can that, you know, a tea can or something that my wife had. And so, you know, is that generally pretty effective if you use something like, you know, I also got this like roll of aluminum tape here, if I can get it to the show and focus.
Yeah.
Something like that. Reasonable, I guess, in terms of a at-home sort of coverage.
Yeah, you could use aluminum tape as a conductive. You could use that. You could put that around any of the open areas. Again, yeah, any type of metal surface. So the cool thing about Faraday cages is that they don't go on the inside of the surface. It'll be on the outside. So one of the properties, electrical properties, is that as energy will flow at the least resistive, and it'll stay at the surface of that material. So even if the material is like, you know, fraction of an inch thick, it'll still be on the surface, and the inside will never get in contact with that energy that's on the surface. If there's enough energy, it'll melt the material, but that's another topic. So if you have, it definitely shouldn't be like paper thin. It could melt, but if it's thick enough where it's considered strong enough that it can handle certain heats, then it should be fine. The energy will flow around the edge. And then again, if you have some kind of opening, if a gap between that energy will, if it's higher frequency, it will enter that gap. If it's low frequency enough, it will be able to jump over that gap and close. So you definitely want to engineer your Faraday cage according to what you're trying to protect against. When we're talking about the HEMPs or high altitude EMPs, it's going to be very hard to protect against those. You're going to need some really interesting equipment. And again, when the event happens, like say I flip the switch and I shoot that energy field, that's the only time that thing actually works. So like, it's the only time you're going to need it. You're not going to need to, you know, after that field of energy flows through and flows around the device, you're done. You could take your stuff out and this works fine. There's no lasting effects unless you're talking about something that's going to be much more energetic and constantly being shot at you. So that's those are the few caveats to think about. And if you leave a door open, or if you open up your, you know, if you have a box and you left it open and you get hit at that exact same time, then you're kind of screwed. So that's where you want to keep your equipment safe. You could keep it in a safe box and hope when you're opening it and using it, no one's going to hit you with an EMP.
So small holes really matter is what you're saying.
Yeah, small holes for higher frequencies. If you have if you're trying to protect against high frequencies, it's okay to have small holes. Or if you have lower frequency issues, it's okay to have small holes. It's going to be very rare to see something that's powerful enough at high frequencies going to affect something like that.
Realize though that if you have a cable running into your box, you're screwed anyway.
Yeah. So the
surface of the cable.
So
yeah.
Yeah. The cable, you can shield the cable. If you have a cable that's going into some device inside of it, it depends on how you're setting up your shielding on the cable. Your cable also will have a shield around it that acts kind of like a Faraday cage. If you have it hooked up to the a surge protector, and the surge protector is, you know, also shielded, and it also has something exposed, you could have some induced current there. But again, it's how you configure your electronics to handle the initial phase of it. A lot of the power supplies, they do have some shut off, but they're not as fast. Like I showed you, the rise time of these things are very fast. So it's likely that your surge protector won't protect you from the surge. It'll probably blow up and not really have time to handle that surge of current into your devices. So yeah.
Follow-on question: what about automotive? You know, we have cars that, you know, like my truck is mostly made out of aluminum except for the frame now, and so is there anything you could do to protect that? Could you have you know, I guess sort of, you know, it sounds like a metal screen, like aluminum screening, probably wouldn't help you much. It sounds like if it's on the bottom of the vehicle. The top, I guess, is somewhat covered.
I guess your vehicle is probably the most susceptible thing about your vehicle is probably the computer and the battery in there, and the computer being there. You know, you sit in your car and you get hit by lightning, it's going to go right around the edge of the car, and you're going to be fine, and it's going to hit your tires and your rims, and it's going to go to the ground. And that's why being in a car is very safe. It's basically like a makeshift Faraday cage. If you're being hit with a lightning, which is, just going right to the ground, if you're being hit with an EMP, it's a different effect. You're talking about broad range of frequencies, it's flowing through things, so it's going to be hard for your car to protect against the higher frequency signals, because you have these open apertures, you have like the holes in your chassis and stuff like that. That's going to go through and it's going to affect your sensitive electronics. Protecting the sensitive electronics, if you want to protect a particular part of your sensitive electronics, like your little computer box or something, you can wrap those around and some aluminum foil or whatever. But these are kind of extensive measures, which I wouldn't recommend. I think you're going to see here that a hemp attack is dangerous, but if your devices are off, if your car isn't running and you get hit with this, you turn your car on right after it's, right after it goes by, you turn your car on, it'll turn on. You're not going to have lasting effects on equipment that's turned off. Usually the effects you'll see is when equipment is on and the induced current is going to create higher voltages, higher currents, that's going to short circuit or cause some damage of the running equipment. Worst case scenario, you have something, a fuse or something blow up, but that's about it. You replace it, after the effect, and you turn it on and it'll work.
Hector,
Is that?
I have a question too.
Sorry, I was muted there, but if you had they have those conductive straps you can have from a car to discharge static, do you think that's beneficial, or do you think that's a waste of time?
To discharge static, so your car's going to discharge to the ground. We have these really interesting insulators called rubber tires. So what's going to happen? It could discharge pretty well. Lightning, because it'll go through the conductive thing to the ground is really not going to do much. I mean, you could probably save your tires if you do that. That way the tires don't burn up. Yeah, because you could probably save your tires.
In the old days,
yeah.
Go ahead.
No, I'm saying that conductive strip to the ground may be used to save your tires so they don't burn, and because the lighting's trying to find a way to the ground, so it'll find anything. But again, EMI and EMP type stuff really won't help at all. I mean, you're really trying to ground your car at that point. The EMP and EMI stuff is going to go right through your car for the most part, and it's going to really matter. Your electronics are going to matter the most.
Yes.
Most electronics, again, have been designed to protect against EMI, and that's why you don't see a lot of issues. But with an EMP type of attack and your car is running, you just may see it stop for a little bit. It'll stop, the battery, the current will stop, and then after it's gone, it'll turn it back on. It has a battery, and you're not affecting anything serious. The things that you're going to see effects on are, there's things like called flashover. If you have equipment that's running with higher voltages, if you have equipment that's running that's very sensitive to any type of signal degradation or anything like that, then you'll have issues. And usually we're talking about like industrial equipment or things that are much more critical to infrastructure. Then you'll have like, fallout effect.
Also, I realize a lot of electronics don't really turn off nowadays. You just have the standby power buttons.
That's true. They'll be turned off. A lot of those smaller equipment. But yeah.
But in general, you have much big. We're getting there's much bigger fish to fry here. If the EMP comes, there's a lot bigger problems you're going to have than just your car not turning on.
Yeah, and I don't think your car will actually be damaged. Like I personally think that the equipment in that car is not going to be permanently damaged, especially if your car is running. It'll probably stop. They'll have the equipment there is not very sensitive. Like you don't have any type of like super sophisticated, unless you're driving a Tesla or something. You should be okay. You should be able to replace some wires, replace some fuses, crank it up, turn it back on with a battery. Okay.
Hello, can you hear me?
Yeah, go ahead. Yeah, go ahead.
In the case of the Faraday covering or cage or so, if you wrap around totally, how do you balance that with heat dissipation or so?
So if you want to cover your that's a great question. That's a problem with trying to put your whole thing inside of like a metal cage, right? If you don't have some sort of airflow, you're gonna not worth it. You could try looking at you know, a mesh screen. So a lot of the high voltage and a lot of the high voltage equipment they have mesh screening. You could use that mesh screening and then create some airflow through that. As long as the mesh screening the apertures in the mesh screening is tight enough where you're measuring that against the frequency you want to protect against. So if you're trying to protect against very high frequencies, 3 millimeters is kind of like the smallest, as the biggest you can have it. You know, fraction of an inch, things like that, you would be looking at protection against smaller, longer wavelengths, not as high.
Okay. So for each equipment, there's only one specific frequency, so you could actually get the hole that you need to accommodate to only one specific hole. It's not like you have a spectrum and therefore you don't know which hole ahead of time or so.
Yeah, that's right. So that's why EMPs are hard to protect against, because you're talking about a much broader, a band that's much broader. So you're talking about protection against lower frequency all the way up to close to visible light, actually. So you have this very large range of protection that you need. And that forces you to create Faraday cages and shielding that is very tight to protect against these high energy, high frequency attacks. And that's where, to just kind of like show you that most of the stuff that we'll see, even if it's not military grade weaponry, or if it's not like military type things, you're never going to see the type of frequencies and energies that we're talking about. So you won't have to protect against those. If you're trying to protect against someone, you know, like someone nefarious trying to like attack you with some homemade thing, they're probably going to be much lower frequencies and much lower energies. And so you probably want to protect against jammers and like, you know, homemade EMP weapons that only go up so high. You can have higher frequencies, but they're not going to be as energetic enough to be able to cause any damage on your equipment. So what they'll do is they'll try to create, you know, a range of frequencies and a pulse high enough that that's really going to affect you at levels where you could protect yourself with just some meshing. You know, a Faraday cage is pretty easy to get. They offer all kinds of protection for devices. So like, if you're really interested in like looking at different ways to protect yourselves, I personally don't think it's a issue because you're talking about an instantaneous event that's happening. Most of your stuff that you're going to care about is going to be off. You may have like an effect to your cell phone. Like someone's trying to like hit you with like a magnetic pulse or something, they're going to affect your cell phone. They'll turn on and off. It won't be something that's permanent. Again, if you're trying to protect yourself against military grade stuff, you're looking at a much a different set of industrial military protection. And I'm going to go into a little bit of that in the next part of the talk, how the government is protecting themselves, the standards that they're using, and what they recommend for industries and utilities and infrastructure to implement. And that's where you're going to start looking at things like these types of facilities where they use concrete and metal and shielding. They use a lot of grounding. They use a lot of surge protection, very expensive power surge equipment. That's what they'll use. In some cases, if you're trying to create electronics that are very resilient towards any type of EMI, you'd kind of cover them in these little, here's an example of a little Faraday cage case around some actual components of a circuit board. So that's what the industry and those manufacturers will focus on. If you're trying to protect your own equipment, it's not as I guess it's not as stringent. You wouldn't have to go to extreme lengths to protect your equipment.
Okay,
that makes sense. So yeah, that's why I want to dispel that. There's a lot of misinformation about how, like, you know, you stick this thing here, put on your tinfoil hat, you know, they're going to hit you with all kinds of weird weapons. It's very rare. I haven't seen that. at this level, I see a lot of attacks at the industrial level. And if you're going to build magnets and weapons that are strong enough to attack that sort of thing, you're looking at military style things, or you have to like, you know, rob a magnet from a junkyard and try to like turn that into a weapon. Okay. Second part, I'm gonna start out, hopefully no more questions. So let's just get into it. We're talking about this weaponized EMP, and most of the weaponized EMP research is around a high altitude EMP. And the reason why is because it's done usually through a nuclear weapon shot at high altitude. Won't cause any like physical damage to the earth underneath, and what ends up happening is you basically get this this EMP effect in a big swath of area without actually affecting anybody, without actually killing people directly. And so this is considered kind of like a cyber attack. Because it's not actually directly killing anyone, even though that's up to debate. So this is much more interesting to folks, and this is kind of why there's like a new Cold War of EMP attacks and EMP threats. The high altitude EMP has to be, another word for it, HEMP, I'm going to use HEMP for now, is going to be triggered around 40 to 400 kilometers above the earth, and that's where you get the most damage. You can drop it closer, but then you get a smaller area. So how does it actually happen? The burst comes in, right? You have these gamma waves, which is being emitted from this blast, this nuclear blast, creates high energy, high frequency waves, right? These gamma blasts are knocking electrons off the ionosphere of the Earth. These electrons are spinning along the magnetic lines of the Earth, magnetic field lines of the Earth. And so when it's spinning around that magnetic field line, again, remember the relationship between magnetism and electromagnetism is this coupled effect. It'll start creating these electromagnetic wave that we could see on Earth as a pulse, on the surface of a pulse. And it takes on this shape. It takes on the shape of a smile. It's kind of interesting, where the red is the most affected and the green is the least affected. And that's mainly because of this interaction, right? You're looking at this polarized interaction. So you're looking at this huge, think of it as a huge EM wave that is going to come in at you at a very quickly, raise up in energy and then trail off. And what you're seeing here is a cross section of that interlocking pattern of the two fields. And so that's why the field that's hitting first, you see at the bottom is this red segment there being the most impact. Now, I'm going to go into, again, I'll talk more about that impact and how that impact affects the infrastructure. But one thing to take away is the breadth of the impact, how you can actually hit a large area, the entire country of America with just one attack. So what is the EMP does not have effect on people, so the initial attack won't affect you biologically. It has no biological effects. It'll go through you. You know, we're not really, we are kind of conductive antennas in a way, but the stuff in our bodies is not generating the frequencies and the energy levels that really are affected by an EMP. The first one that was kind of observed, specifically a HEMP, nuclear detonated device, was in 1962. The U.S. Observed this on the Pacific Islands. The Soviet Union was actually testing, and they launched this nuke in the air, and they saw it. They weren't intending to try to do an EMP or anything like that. They're just testing nuclear effects. And when they did that and they launched it in space, what they noticed was that everywhere from the Hawaiian Islands to Pacific Islands, all these islands were being affected by this energy pulse, and everything from street lighting to circuit breakers were just being triggered. And they were basically trying to look at this new effect, like why is this nuclear blast causing this EMP-like effect? And we're going to talk a little bit about what actually happened there. But that was kind of like the first foray into this capability. And since then, after the 1962 testing, we've seen governments look for ways to understand what happened, how to protect against it, and see how that has been evolved. Now, EMP itself, the HEMP itself, is going to be in 3 parts. We talked about the rising edge. That rising edge is called an E1 component. That rising edge is kind of like a electromagnetic shock. It's a very fast lightning-like effect. And then that E2 component, that peak area, is going to be also like a lightning effect. And that E1 and E2 is very similar, and they're about, I think it's a few seconds away from each other. Yeah, it's a fraction of a second away from each other, and you're going to see them both hit. These are the things that are going to affect sensitive equipment. This is that very similar to the EMP, low-powered EMP, when you just create a pulse of energy. It's very similar to that, but imagine that an entire area all at once being hit with that. And then there's an E3 component, which is the slow rising effect of this tail. It's kind of like a slower decay. And what ends up happening is that slow decay is dangerous primarily for long transmission lines, things that have long conductors, things that have that spread very far. It's more area for this massive amount of energy. Excuse me. It's more effective for this massive amount of energy to actually induce current into these lines. So that current induction is what we're going to talk about. That seems to be one of the key reasons why HEMPs are so dangerous. They will affect that area with that E3 component. But the good thing about the E3 component is that it's much smaller in impact than the E1 and E2. And you see on the left here, the E1, E2 kind of spreads across very, very nicely from Miami all the way to like Canada. And the E3, the slower moving component, is only affecting that area around Chicago, Washington. And so that kind of shows that it's a much more focused attack there. And a little bit of the attributes of this. The lightning, if you take lightning, for example, it has a broadband, like the frequencies that lightning emits, the frequencies of energy that lightning emits, only goes up to like the 1 megahertz to 10 megahertz. But when we look at the E1 component of the HEMP, we see that it ranges from 10 all the way to 300. So what this means is that the equipment that we currently have, okay, the equipment that's currently protecting against lightning effects, lightning strikes, lightning EMI, lightning pulses, that magnetic pulses that come from lightning, the equipment that we currently have installed in the infrastructure can handle that, but it's not able to handle this extra higher energy, higher frequency impacts. And at that point, then you start seeing some degradation on the equipment. And so the standards are not really built around the E1 HEMP. They're built around the lightning, for lightning protection. And so that's one major difference. Another thing that we look at here is that the E1 and E2 have this really quick rise time, right? You're talking about like nanosecond rise times. And then you have the E3 that lasts about maybe 1 to 2 minutes. There's a blast, a 10-second blast, and then this heave that they call a heave, this E3. And that lasts about 2 minutes. And those 2 minutes of induced current into these long transmission lines and this huge equipment is what's going to cause equipment to fail over time. So basically, overloaded power lines, overloaded transformers, things that just can't handle those 2 minutes of just charging and energy coming in will cause degradation to the equipment. So a combination of equipment not being rated to handle above lightning standards, and then the E3 component of these 2 minutes of just continual discharge will cause degradation in the equipment. This table shows the attributes of HEMP versus geomagnetic disturbance. So the geomagnetic disturbance is the solar storms, the solar flares, the things that will come off the sun that will affect natural occurring type EMP looking things. Now it's very important to look at the two differences. So I just talked about the E1 HEMP, the E1, E2 components, which is that quick blast that comes in, and then the E3, which is a more focused attack. The E3 component is going to be very similar to what we see naturally occurring from these geostorms. So I'm going to look at the geostorms first. I'm going to look into a little bit, I'm going to show you guys a little bit of what has happened in the past with geostorms and how these phenomena, how these things have been responded to by our equipment and our infrastructure, how the equipment and infrastructure actually was affected by these geostorms. And that's where we see the most learnings from, is looking at how E3 affected our infrastructure and seeing how we can combat that. E1 and E2, that's a different method of protecting against that. That's more of the Faraday cage and the shielding and the quick impact. We're trying to protect against that initial blast. But what's really important is that E3, how do we create an infrastructure that can handle this E3 discharge? So the vulnerability of the infrastructure is quite clear. I think everybody knows that we're very interconnected services. So power plants go down, you have, fuel supply goes down, communications go down, all kinds of things start being affected. The threat of these HEMPs now is bigger than ever. As Rod mentioned, North Korea, rogue state, even back in 2004, we've been looking at how North Korea launching these satellites. The first 2 satellites that they actually launched were actually right over America, and kind of like a warning shot saying, well, we could launch a HEMP if we wanted to. This is something that's everyone's known since the 1962 test. These HEMPs are possibly much easier to implement, much more notorious to talk about, much easier to like infiltrate. So you could actually get like a hot air balloon, or you could set it up in a little submarine, whatever it is. As long as you can launch it in space, you don't need any type of rocketry. You don't need any type of like advanced ballistics. You can just like float this thing up there, and it will actually create damage. And technically nobody will die, but you will have a blackout that could disrupt markets, that can allow for enough time for somebody to come in there, create some sort of cyber attack, and that's what people are really looking into. So in 2004, there have been reports from the government talking about these things. And Peter Pry, Dr. Peter Pry from the Blackout Wars, he has written that book, but also he actually submitted an entire nuclear EMP attack scenarios and combined cyber warfare document that I researched a lot. And it goes into a lot of different scenarios. Here's on the right, you'll see a snapshot of what it looks like, an EMP world war, what that would look like. He starts out with different things like, hey, what happens if Iran attacks Israel, Iran attacks Egypt and Israel? What do these things look like? What if ISIS attacks Italy? What do these EMP attacks look like, and what are the fallout of that? And considering that we're one of the most technologically advanced countries on Earth, we're such a huge target for these smaller, less advanced state actors to inflict damage with an EMP and not actually technically have to have a built-out ballistics program and nuclear program. So another thing of concern here is there's a lack, or there's a observation that awareness, planning, training, and testing is very important to be able to handle a HEMP attack and any type of state actor cyber attack. So one of the nice books that I was able to review is called The Grid by Gretchen Bakke. She gives a really awesome understanding and very like plain illustration of the grid. It's one of the best books I've read on the grid and how the grid was formed, and it's very accessible to most people. And she talks about how it was created, and monetization of it, and how we support it. And one of the things in there is talking about like the Queen's blackout, and how people like Con Edison wasn't able to really handle that blackout very well. And the lesson learned around that was that there was just not the right communication. The planning and training wasn't there. There was a software bug in the system, and they just kept on ignoring it. So training the right operators to kind of realize that there are events happening and blackouts happening and things happening that they can't really understand is different. And it's harder to train for things that are very rare than just in day-to-day things. So this is one of the challenges with a HEMP attack, is that it's very rare to see it, and so it's very hard to find people trained and aware to know what to do about it. So the E3 component that we talked about, what does that look like? What did it look like in the past? So E3, again, looks like a geomagnetic storm. And according to some carbon-14 dating on rings of trees, and there's some signatures in ice core signatures that we could look at to look at this beryllium 10 and carbon-14, and we could see the cosmic coronal mass ejections occurring all the way back to 774 CE. So this is something that happens all the time. And this is something I wasn't really aware of until I was doing this research, is that we are constantly being bombarded with this solar weather. And sometimes we see the effects, and sometimes we don't. In 1859, that was like that Carrington event that Rod mentioned. That's where things were really like interesting, because apparently the aurora borealis was seen across the entire world. There's people writing down in their diaries saying, hey, look, miners waking up in California to like the light, thinking it was the daytime, and it's really just aurora borealis. And you're seeing telegraph pylons with sparks. You see people being able to send telegraphs without any power supplies. There was so much energy on those lines. So there's a little clip here of a recorded Carrington actually recorded on the magnetron these events, and he was able to like kind of say, hey, this is what happened, and he understood what actually was going on. It was this huge solar flare that affected the Earth. So we noticed that these things kind of keep going. So in 1921, there was another storm that occurred that was pretty significant, very similar to the Carrington event. And then there were others, Easter Sunday storm, space age storm, and then kind of culminating to the Hydro-Quebec grid storm of 1989, this is the best one I think that I found, because it actually has imagery of a blackout that occurred. It lasted 12 hours. It only took 2 minutes for this blackout to happen. And mainly it was because these long 735 kV power lines were stretched across Quebec. And there were actually points where the Quebec Hydro didn't really have anywhere to handle this extra load, this extra energy. They didn't know where to sink it. And one of the basics about electricity is that if you generate energy, you have to source it, you have to put it somewhere. Very similar to that lightning we talked about. If lightning comes and hits your car, that lightning wants to go somewhere. And if it's not through the wheels, and it's going to go through something. And it's easier for it to go around the metal around the outside of your car and through your tires than it is to go back through air, which can also be a conductor, and that's why lightning breaks down the air conductivity and hits your car. It's easier to go through the car manifold than through air again, through the cabin, and then back to the ground. So it's going to find ground, it's going to find somewhere to sink it. And very similar, when we generate electricity, we try to give it to a load, we try to give it to somebody to run, to turn on the lights, to do something with it. And this grid just got this huge surge of energy on these lines, and it didn't know where to put it. So a lot of equipment meant to hold it and send it down was just being burnt out. A lot of the power lines were rated for a certain amount of voltage, and they were just going over that and causing harmonics and distortions in the line that just caused them to break down and burn out. So these events happen, and then when that happened, you start seeing things just shutting off. And so you start seeing these islanding off of the grid and different equipment just shutting off to just protect itself. Also, the things that were getting energy now are no longer getting energy, and so you see this blackout occur. And if you see in the corner at the right, you see this red circle covering that entire blackout in the region. New England Power Pool, New York Power, they both kind of went down the same time. They learned about this. They made a lot of changes to the way they actually handled power. They were no longer putting the same amount of power on those lines after this event that they had before. So this is kind of like allowing for the capacity of more to go in there if it happened again. Another key thing about this one was it was such a big storm that even satellites in space were just tumbling out of control for hours. It affected a lot of space communication. And they said the reason why this is really important is because the northeast of our continent has so much igneous rock underneath. It's very hard for that rock to absorb the energy. And so you see a lot of the energy just staying in the air, looking for something else to cling to. And a lot of the stuff that was in Quebec was these lines that were just stretched out, these high voltage power lines stretched out around the region. So that's the Quebec hydrogrid event. Ever since that, I think they did a lot of upgrades to their equipment. and so did the U.S. And the reason why I say that is because in 2003 there was a Halloween storm, and this thing apparently had aurora borealis. You could see as far as Florida, and the effects in North America were almost non-existent. And what we really saw was effects in Sweden. Sweden lost power. A lot of local municipalities had issues with their power. A lot of effects happened similar to what we saw in Quebec around Sweden. So they said, what happened with North America? It was fine. Nothing really happened there. And they had two theories. One was, hey, they really weren't exposed to the substorms that Sweden did. Sweden had a lot more, was more focused on them. The storm really hit them harder because it was focused and kind of lingered around that area. But also, there's some comments around maybe the American electric grid started becoming a little more resilient, more robust since 1989. And so the measures that they put in place to reduce the capacity of the standards they put for the power lines was much better. So they were actually able to handle and ride some of the storms around. The equipment was also able to handle the extra loads and turn themselves off and kind of shut off and reorganize. So a lot of that did occur during that time. So that's why it seemed like the North American grid was a lot better fare after that. But also in 1989, around that 90s time, in 2001, there was a lot of regulatory government agencies that came in to help out, and they were very afraid of the capabilities of other people using HEMS against them, and also the effects of a geomagnetic storm on the grid after the Quebec hydro. So there was a combined effort between the ESA and NASA to start monitoring these solar flares. The FERC and NERC got together and basically said, hey, go ahead and start looking into how to protect against these things. How do we create better systems for it? And then the NRC, which is a nuclear body, they look for ways to protect themselves when they have nuclear equipment that they have to protect with no power. Like, how do you take care of those rods and stuff like that? How do you make sure that you can still handle a nuclear power plant without energy? So 2001, there's this thing called the EMP Commission, right? And this is, I think it was Trump or Obama age, but they ended up creating a document that had all of this recommendation involved in it, and they looked at, what are the threats? How do we fix it? What are the threats to the grid? What's the threats to telecommunications, and how do we affect it after the 1989 Quebec storm? So they came up with Volume 1, 2004, really good report. A lot of people read it. It kind of, Dr. Pry kind of was architecting a lot of this stuff. And in 2006, they were reestablished, and they came out with an even better report in 2008 that actually had a lot of simulation involved. So they went in, they actually did a lot of this stuff that was theoretical, and they actually implemented labs. They looked at equipment, they looked at the effects of the equipment at the same ranges and power levels that you would see with a HEMP. So what did they find out? Cell tower, power lines, those things, they looked at that. They looked at the effects of power relays and how these power relays can be robust enough to actually handle the impact of a HEMP. They found out these things are good. Like these power relays can handle it. The problem is that they need to be reorganized. Like the configuration of where they are needs to change. That some of them were just too close together and they were just not redundant enough. So the increased redundancy would have helped. And also they found out that SCADA systems were just not there. A lot of older legacy equipment, if you guys are aware of SCADA, SCADA stands for Supervisory Control and Data Acquisition. I worked with a lot of SCADA systems in my time, and really these SCADA systems are kind of, once they're built, they're never touched again. They're operational technology that's meant to be kind of like a machine. They set it up with a steam turbine, and they say, never touch it again. Just keep it running, don't mess with it, it's running fine. So the technology, though, never gets upgraded because they're afraid of the impact. Also, there's a lot of regulation around upgrading the power plant. So you don't want to mess with stuff. Every other day, a new system comes out, a new program comes out, or a new connector comes out that's better. You want to make sure that that thing isn't going to cause risk of cybersecurity issues or even functional issues. So these SCADA systems never really got upgraded. I've seen SCADA systems with like Windows 95 on them, and the other thing is that the connectors that these things use, they usually talk in serial to the devices that they're talking to. So if you have this old steam turbine, it'll be a serial connection to that steam turbine controller, and that serial connection is very susceptible to the E1 and E2 components of the EMP. Their RC32 ports just don't handle it. The serial communication is just not shielded well enough. And so even the programmable logic controllers, the actual things that actually have the code that keep the turbine in a control state that makes sense, they are susceptible to flashover, where they can have components that weld each other, that can jump and spark and cause issues where they change either their programming or their programming just stops running. So that's the note there. And what ended up happening is that they just said, look, the best thing that you have there is maybe the power relays. There's these power relays are just like these big electromechanical relays that you kind of snap together, and they're like these mechanical switches. And those things are needed, and they're very, very good to like island off different sections of the grid. So these things are very robust against an EMP. E1, E2, and even the E3 components are fine. So the islanding component, the islanding feature of the grid is still very robust against hemp. But as soon as you island it off, your equipment's going to be fried. You guys need to figure out how to do better communications and figure all these other things out. So the end result of that report, 2008, was that the power grid is vulnerable to collapse due to the E1 component of the EMP. And you're not even looking at the E3 yet, just looking at the E1, because they think that the E3 is not going to affect those power lines because of the changes they made to the power lines, the use of the power lines, and because of the strength of the electromechanical relays. So in 2008, they had to protect the high value assets, assure communications, protect emergency power supply, because you want to make sure that if you have a diesel generator or something that you need to keep power on, you want the fuel and the logistics there of a blackout, you can still power that thing up. Separate the interconnected systems. So what they meant by that was that there were a lot of, the entire grid has different regions of operation. And so there are some systems that are single point of failures. So having those interconnected systems separated, you can create more islanding and therefore create more resiliency in the grid. And they went from, in 2008, they had about 2 or 3 different initiatives there that they did go off, and they basically reformed certain companies that were actually going to separate those connections. So in, I think about 2015, I think a lot of that interconnection was figured out. The black start generation, what does that mean? So black start is kind of like, it's kind of like a backup generation when, for example, you were talking about your computer, right? When your computer shuts off because of EMP hits it, let's say everything turns off, blackout. Well, if you go in the back and you grab yourself a bunch of batteries and you duct tape them together and just turn it on, and now you can turn your computer back on. So black start is very similar to that. What they usually use is renewable energy, either hydropower, because it's very powerful and very constant. So as soon as the blackout happens, you go off and you flip a switch, you get a big waterfall to turn a wheel, and you basically create energy from that waterfall, and that feeds back into the grid, and then you start using that energy to turn on your steam turbines again, to turn off your, turn on all of your large rotating equipment. And that brings the grid back up. The more generation you make, the more load it could take, and people get their energy back. So that black start is kind of like a primer that you can kick off in emergency situations. The EMP response training, again, is very important. There was very little EMP response training back in 08. And I think since then, there's been a lot of standards and a lot of documentation around that. A lot of the organizations like National Research Energy Labs has done a lot of communication to the utilities about EMPs and how to protect against, how to train and protect against that kind of attack. So a lot of the systems are designed around that now. A lot of segmentation of generation, segmentation of responsibilities, segmentation of, hey, this happens, does that person have the power to ignore this alert or not? And how do you make sure that the right people with the right level of information get it as fast as possible? In 2019, so the EMP Commission continued to pull out these reports, which is great. I found a lot of information that was right from the EMP Commission. A lot of great stuff. This is being kind of a joint effort by the cybersecurity and intelligence community. They provide this information. They invest money in this information. They continue to update it. The latest document is a 2019 version. I have on this deck, there's a GitHub link to all the hemp document library, and you guys can browse it, all of the notes, the meeting notes, the research, and all of the simulations and the models that they've created around the references is there, so you guys can check that out. Sake of time, the idea here is level 1, level 2, level 3, level 4. People choose what is the best. What are the things I need to do to protect my equipment? And this is mainly for the industrial community, the infrastructure community. Well, level 4 is that military spec level, where if you got it like this, you're good, right? That's what level 4 is. Level 1, 2, and 3, depending on the size of your equipment, the impact to actual people, impact to logistics, then you can choose to implement the lowest cost solution or more costly solution where you only need like minutes and outages are permitted. So it ranges from unplugging your power and keeping it off if it's not necessary, to implementing hardening, 80 dB hardening on your equipment, or like a shielding that is a very high power, high frequency shielding. If you notice on the right, you see things like 80 dB hardening to 10 gigahertz, which is a very high range of frequency, meaning that you would have almost little to no apertures in this shielding, and it has to be incredibly powerful, or incredibly strong to handle that type of power. So again, there's more recommendations. The 2018 reports really dive deep into what they can do. They discuss about disaster recovery and how to keep that communication going. And I'm gonna switch gears here. So after all that recommendation, they do also talk about the idea of these hemp-style weapons, right? So we talked about the radio frequencies, lightning can cause EMI, and E1 hemp. That E1 component can be created by these, can be simulated. We talk about the low power EMPs that can kind of have an effect. But now we're talking about the military grade standard weaponry that you can create that will have similar effects like an E1 component of the hemp. And this is where if you come across this is where you would see it in like the battlefield or something like that, where these things will actually affect equipment. You would affect communications, you create jamming, you could probably use this against drones. This is the type of stuff that you would want to look at. So this is where you're talking about very high power, very high frequencies, very strong, very portable equipment that you could use against state actors. So you have like a munitions damped sine EMI generator. You have a Russian device here, it's called a hyperband pulse generator. You even have, just look down, Sweden's hyperband generator, and then you have the Jolt hyperband generator from the US. Each of these having similar components to what the E1 would do, but they're not, some of them have more power than E1, some of them have less frequency ranges, some of them change. So they're all kind of designed very differently, but they all simulate that type of E1, E2 attack style. So how to protect against those types of weapons? The military looks at, hey, you guys should have really well-crafted buildings. You should have ferrite choke on your wires. So we talked about, hey, you have an exposed wire. Well, ferrite chokes are pretty good protection against those exposed wires. These things will actually dampen any type of induced current, and also slow down that increased current rush. So that rush of current that will come in, it should slow that down. That way your surge protectors have time to kind of, shut off any issues, shut off your equipment. The EMP shielding, if you have concrete, that's the best. That attenuates any type of energy that comes in the most. And if you see here in this bottom where the shielding of the building, it's always best to have all metal, no windows. that's the best attenuation. That's where you have the best one. And obviously, good, moderate, poor, that's where you're going to see things like if you're a civilian and you want to, protect, have a little type of like protection around something, maybe you want to look at, okay, I have a metal siding, no windows, kind of like hut here or whatever, and build a little shed there to protect against that. But that's the kind of, that's only going to attenuate you 10 dB, and then 30 dB is where the military is going to look at, hey, this is very critical infrastructure, we want to put it into these very locked box style buildings. If you look at the bottom right, this is really interesting. This is kind of like a diagram proposed by the Department of Homeland Security, and it shows a control facility completely locked off where they have metal cabinets. They have this this wave guide, entranceway wave guide. This is kind of built in the idea that you actually can direct waves and keep your entire facility shielded. So you can actually build this out of metal and make it an entire building. So you don't have to actually, be in a tiny box. You can actually build this into the entire infrastructure of the building. For the most part, a lot of control systems nowadays for utilities and generation fleets, ones that have nuclear generation and ones that have have control over large megawatts of the grid, they design their control centers very similarly. They look for how to segment the physical barrier, and also logically they segment the access to the generation. Closing up here, again, hardening against HEMPs. We're looking at RF shielding, aperture treatment, electrical penetration, and grounding. That's mainly what it is. This is a military spec. And now, kind of finalizing all of this information, all the recommendations that we got from the government, all the recommendations we got from these research labs, kind of point to this idea that there should be these things, these initiatives should be taken on by these facilities and by these companies. So EPRI, which is a Electric Power Research Institute, an independent company, worked with the Department of Energy and other research labs to include the utilities. So look for utilities and power generation companies like Duke Energy, NextEra Energy, FPL, PG&E, all these different AEP, all these utilities came together and they started opening up their books, opening up their their equipment and saying, hey, go ahead and look. And this is where EPRI started doing tests, looking at what they could find. And they noticed that a lot of the equipment has been upgraded to the point where the effects of like an E1 or E2 really don't have that much of an impact to some of the redundancies put in since 2001. So SIP has been a very interesting component of that, and the NERC-FERC standards have also been applied heavily, especially in nuclear, but mostly in fossil plants and renewable energy around the country. So what does that mean? I think, end of the day, the EPRI research was pretty interesting. When I was looking at it, their research shows that blackouts will occur with a HEMP attack. They will occur, but what ends up happening is that because of the power lines and now the islanding of these of this equipment, you're going to have transformers that blow up, but they're going to be isolated. So we look at the worst case scenario where you have hitting the entire country. If it hits the entire country, the E1, E2 effects will look like lightning attack, right? Like a lightning strike. But it may have, it may flicker, lights will flicker, things will happen. And if you do have a blackout, it'll be because that particular segment of the grid will now be islanded off. So they learned that the ability to island off has improved a lot. The equipment is not military standard equipment, but it is hardened enough to handle an E1 and E2 event. And then the E3 event is also a non-starter because now what we've seen is that the E3, after the testing, those power relays have been dispersed and the capacity on the lines have been reduced. So the standard now is that you actually have a much lower capacity so that if it does affect, you're able to handle that initial 1 to 2 minutes of charge from a HEMP attack. So yeah, EPRI had a very positive look at it. The caveat there is that they did not have a full understanding. So we're looking at what their research gives you is they look at what they could look at from the utility, but I think it was only 5 years of research. And from my experience, a lot of times they will provide to them the best look or the best facilities to look at, the best power plants to look at, the most invested places to look at, and they'll send them out there. And then they'll take their notes and say, yeah, we have this redundancy, whatever. But I think that there's still caveats of the United States electric grid that are still antiquated. And so what you'll see in a worst case scenario is you'll see maybe pockets of blackouts that last for, I don't know, a couple hours, few hours. Depending on where it is, if you have it in areas where like PG&E, who have a lot of issues like with fires and with redundancy, because there's a lot of like issues with their grid. They have a lot of vegetation, a lot of things go down, and when they have blackouts, it's really hard to like roll trucks out there to figure out what's going on. If things like that happen in places that are not prepared, like certain regions, the blackouts would stay around for a while. The good thing is the Northeast side has taught us that even with an E3 event, you can actually bring up the power quite easily because of the reserves now in the grid. So all in all, there is not a huge alarm. My summary is that there's not a huge alarm to hemp attacks on the grid today. I think the more nefarious thing is targeted hemp attacks. If you have a targeted hemp attack in a particular region, that region can be down for a long time, and you could also combine that with cyber attacks and cause significant more damage and to equipment that cannot be replaced easily. So just to cover it, EMP is electromagnetic phenomenon. HEMS come from nuclear detonations in the sky. HEMS are a weapon of choice for rival countries. HEMS have this E1, E2 component that look like EMI. And HEMS have an E3 component that is where the nefarious part of it that looks a lot like solar storms. The grid infrastructure today has become much more resilient to these things. From my research, the hemp attacks can now, a large scale hemp attacks are not as worrisome, but focused hemp attacks I think are still an issue, and there should be more research into focused hemp attacks. The attack vectors of this thing, if you just think of hemp by itself, yeah, but if you were to combine it with a coordinated attack with cyber attack, you just need to turn off the lights for a few minutes to insert something or to be able to rewire something or just get past an alarm system. So if you look at this, and also the idea that we have data centers and reasons why people would try to get into our data centers, and can these data centers handle these types of events, I think that's a different angle. And so combining the grid vulnerability with data center vulnerability will probably be something that people are going to be looking into in the future. Acknowledgements. Thank you, Rod, for this. Thank you, HackMiami. You guys are awesome, and thank you for helping me organize this event.
Thank you. Thank you for being here and for helping us. That was a very thorough presentation, and I truly enjoy it. I have a question for you. If I fly all the time, what happens if one of these things happen? Are planes resistant to these things, or? So the reason why they tell you to shut off your phone on a plane is because they think they have a very sensitive electronics on the plane, and they could change the navigation on you, and the EMI could affect the navigation of the plane. But I'm very skeptical of that. I think planes have much more resilient electronic components on it than they tell us, and because they didn't need that stuff before, and they still had the same planes. EMP on a plane would be interesting. Like if you're flying by one, I think you would have the lights would go out on the plane and the navigation would shut off. I'm not a plane expert, so maybe there's like a manual override that pilots can take on and start flying the plane manually and glide out of that region and kind of like flip the lights back on. But yeah, that's a good point. I'm not sure what the impact would be. I know that there would be some
significant impact to the navigations of the plane.
Hector, Rod, can I say something about that?
Yeah, go ahead.
Basically, while I was working at Raytheon, we have a lot of network switches, and they also have to be Tempest and HEMP tested, right? So I dealt with like Faraday cages like crazy. I know for a fact, like Air Force One, the president's plane, the vice president's plane, and the National Airborne Command Center, the NAOC, they do get frequently tested against electromagnetic like weapons. They literally sit right under a actual electrical grid, and they shoot the plane with actual pulses to test not only like navigation, but also electrical systems inside of it. So
okay,
they frequently do it. Now, where or how often do they do this every year? I learned a little bit of that, but it still remained a mystery. But I would safe to say it's classified to a certain extent. But they do test these, at least on military planes. Now, for a civilian plane, it's kind of hard to say. It's kind of like what Hector said. Like, yeah, you'll have some like electrical interference, navigation, like the GPS will start freaking out because you're inducing an electromagnetic field that could very well interfere with the GPS system altogether.
Yeah,
but
you'll probably have like commercial. Sorry, go ahead. You probably have commercial components in the airplane, so those commercial components are probably not going to be military standard grade. They're probably just whatever they can find. And yeah, and there are standards around it, but from my research, I think the airline industry is very behind on cybersecurity and even like standards around protection, electrical protection.
I was just wondering, by design, of course, most of these planes, they're already $200 million or more or so. But looking at the design, like a cylinder, perhaps mostly made of aluminum or whatever, and they already caged or so. At least one would think that the cylindrical aluminum that is wrapping everything all around, doesn't that already provide some sort of protection?
Yeah, so what we're talking about here again is the Faraday cage feature of the cabin of the plane. It's good for up to certain frequencies. So like even the hole of the window, that's too big, right? So that even if you had like a half a foot, right? Now you're talking about frequency ranges that the EMP has a lot of energy in. So it goes all the way to like 3 millimeter, so you're talking about like up to 10 gigahertz, right? So like you're looking at 10 gigahertz is incredibly small. I think it's in centimeters or nanometers, centimeters, all the way to like 1 foot. So you're looking at a huge range of wavelength. So all of that is being passed through the plane because it can't be shielded in the outside of the plane. So everything outside of that range, like anything lower than that, will be shielded around that Faraday cage. But the windows will allow energy to flow through. And if you do not have shielded components inside of the plane, they will be affected at some level. And depending on how far away they are from the initial blast, they'll have some level of impact. And again, this is interesting because it's the inverse square law. So the further away, the less it's affecting you. So you got to think of the attenuation of the energy.
I have a question. So how about at home? What can we do at home? Is there anything we can do? Can we use, somebody told me once that you can use your oven and wrap things with aluminum foil. Is that true, or is just a oven?
Yeah. Again, Faraday cage is the most effective thing around it, but the problem is that it's passive, and if you have, maybe you have 2 minutes and you see like, hey, there's a nuclear thing above you that's gonna blast off, you have the time to go ahead and stick stuff in an aluminum, aluminum box or your oven. You could try that. Again, if you don't have like an industrial level type of protection around those things, it's going to be very hard to protect yourself against the majority of impact. Again, it doesn't affect you physically. It won't affect your stuff physically. If your stuff is off, it's not going to affect the stuff that's off. It'll probably affect the things that are on. So you're not looking at a, you know, like kind of in the movies where it's like all your stuff just explodes or whatever. So it's going to be a passive, just like your lights go out, flip the breaker and you're turning back on, hopefully.
I've seen the tactical bags sold in commercial places that cost in the $300 to $400. So
Yeah.
will it be sound for, just like we have batteries, right? We have radios. We have HackMiami. We all have radios. We have alternative channels. Ray gave a presentation on how to charge cell phones with batteries. Will it be sound to invest the money in something so expensive and put there a burner, a computer that probably you don't use, or something like that, and it's the case of an event like this? If
you were serious about, like, if you were doing something where you want to protect yourself against something like this, I would get like an aluminum box. Get a box. Just create a box out of wood. Put aluminum around it, inside or outside, or get a metal aluminum cage and build it yourself. As long as it's completely closed off. Yeah. And then you just stick your stuff in there. But again, if your laptop is off and it's fine on your desk, it's not going to be affected. If it's on and you have some sort of current across it, then it's going to be affected. But if your equipment, like, let's say you have a cell phone emitting something, like you have a cell phone, you don't want that cell phone to turn off, you stick it in that cage, it's going to keep running. So that's the one good thing. Let's say you have something emitting some Wi-Fi signal, and you don't want that thing to go down even through an EMP. Then you can put it in a cage, a mesh. I don't know if it's gonna emit your stuff, if your holes are. You gotta engineer it. But at the end of the day, it's gonna be interesting to see. I don't see the big benefit in investing in that. You could. I don't see a big benefit investing in that. It's kind of hard. It's kind of hard to see a good application for it unless someone else has an application that I can. Go ahead.
I was going to say some of the things I've seen are where people would take like a metal trash can, and they put their real critical electronics in that trash can, and then take some of that, that foil tape stuff, and go around the edge where the lid goes on, and then that way you do what you can with fairly cheap methods. So that's one way that some people, and sometimes they'll put stuff like they may put some radios in there too, so that, because you can imagine a lot of communications may be down, like your cell phone may not work anymore anyway, so you might want to have a couple FRS radios in there if you want to communicate with your family down the street or something.
If you want to keep them from ever getting damaged, you can stick them in an aluminum box. Maybe the antennas will pick up a lot of energy and then kind of fry something in there if it's not a very sophisticated device. So stick them in an aluminum box. In an aluminum box, and you avoid that ever happening. And then when the first wave goes away, you have this thing and it's perfectly pristine and never been affected by any type of energy wave.
Another thing to keep in mind, some of the things when I was looking into this was that, if you're in your car and it's powered up and running and we got an EMP, think about things like make sure you got some good walking shoes, because your car may be dead and traffic maybe go to a standstill because a lot of other people's cars will be dead. And so if you at least have a good pair of sneakers in there, some water so you can get out, maybe think about, how you're going to get around. And then of course there becomes, if that happens and people can't get around, there could be a lot of social unrest issues there too. So you got to kind of be prepared for that.
So to make this clear, if the computer is not plugged, the computer would resist this? Not?
So the impact, the danger of an EMP is the overcurrent of energy, like over induction, like getting more energy than it typically can handle. So when it's not plugged in, all you're doing is giving it energy. Typically, it's really hard for that induction to happen to turn the whole system on. And turn it on and then even like fry stuff. It's going to be very, from what I could tell from the research I did, that's something that will most likely not happen even with the E1, E2 type of surge. what will happen with the E1, E2 surge, anything that's currently turned on could get over voltage and cause it to fry. If you have very sensitive equipment, if it's sensitive where you don't want any current on there because it'll recalibrate a GPS sensor or something like that. That stuff can get out of whack, especially if it's turned off, and you have like this energy come in. It can create enough energy where you either flip a bit or recalibrate a setting like enough. Some devices actually hold current when they're turned off. They hold a little bit of voltage in order to kind of, for example, like certain memory actually holds voltage, right, when it's turned off. So that could be zapped with energy and you can kind of lose it. So like random access memory that's being held in some state can get zapped and you can change that. So that can change stuff. That's the kind of effects you will see. Read-only stuff, like things that are not powered, you won't see a lot of effects on it. Things that have just wires and they're very clunky, they need a lot of energy to turn on. It's going to be hard to see the type of voltage and type of currents induced into those systems in order for them to be fried. That's why a computer like a server will not get enough energy to power on 2 amps and turn on your motherboard and turn everything on. That being said, the things that I saw in the geostorm, like they had power enough to like do a telegraph, it's because the lines had energy in them and they were just able to send signals on it. You won't get that kind of enough energy in the small package and small devices, especially like in a computer, enough energy to actually turn on.
Well, another thing to keep in mind. I'm just going to say another thing to keep in mind too is that in this situation is that a lot of things, especially in Florida, we have a lot of our flood control things that have systems. They're probably going to be powered up, right, at the time. And you also have, wastewater treatment plants and the pumps and those kinds of things that are electronically controlled, with RF sort of things too. So you kind of got to, I don't want to be a doomsday guy, but I would say just keep in mind, there are a lot of things that probably won't work, even if the power grid has gotten better and we're better about how we distribute power and the relay systems and those sorts of circuit breaker things. There's still a lot of other things that may not work. And you kind of want to think ahead. I always think of an analogous to like hurricane prep when you don't have power for a week. It may be a long time because if those systems don't come back up, then, it's going to be, Florida without air conditioning, is going to be unpleasant. If the sewer system is pretty unpleasant too.
So to adjust the pumps and you're referring to the control systems for the pumps and things like that. So typically, like most pumps are, if you have a controller for a pump, have you ever seen like the switches on your sprinkler, like the older ones, or like mechanical switches? So like they actually have, you can like wheel them back and they kind of click, and then once they get there, you turn on your pump. So there's a lot of systems like that, especially in water facilities where they have mechanical switches for things. Also, there's a lot of them are set to, if current of a controller is set to off, those systems actually they go to states where they're safe. So they actually go to states where things either are stop flowing, reduce current, reduce pressure, and they will go to safe states at the lack of energy or the lack of current. Sometimes they're like dead man switches where you have energy, the heartbeat's on, you have these systems, these sensors that are currently saying things are working. Most sensors will have some sort of trip switch where it's like, hey, I'm no longer working, I don't know what's going on, and that would already be set to some sort of like a mechanical way of actually shutting off that pump. So there's systems in place today. I've seen them in place in power plants, in place in water treatment facilities. I've seen them in place in industrial settings that are designed for worst case scenarios. So energy stops, things safe, shut down. What you'll see when that happens, what you'll see when that happens is not the fact that things are broken, is the fact that they're stopped for a reason and people just haven't gotten around to turn them back on. So that's where you have your blackouts. That's where you have your, your water's not running or whatever. You'll have people say, hey, I haven't gotten to you yet, because if I turn that on and there's a down power line in the middle of the street, a kid can can run into it and die. So I got to go over there and make sure that there's no down power lines. Make sure that there's, before I do that, I have to flip the switch, I have to make sure nothing's broken out there. So that's where the blackouts are going to take some time. But once the technology today in the grid is they call them their automatic surge protection devices, where they actually try to find the fault within two lines. So like your neighborhood and the neighborhood next to you. Let's say the neighborhood next to you has a tree in the middle of the power line. Your neighborhood would have to switch its connection to a different distribution system and get the power, right? And then you'll be fine. But their neighborhood where that power line is down, they're going to stay off until they can fix that tree. But they don't know that yet. So what they do is, back in the day before the grid was smart in Florida, they had the entire section off for weeks at a time until they fixed that tree and they turned it on. Now each one of these devices are remotely sending information through cell towers, cellular networks, and they basically say, yeah, there's a way to route this thing over and isolate this fault. And so now what they're doing is they're able to route energy and kind of isolate systems. And so the blackout will stay where the blackouts are affecting physical infrastructure. The blackouts will be redirected, or the energy will be redirected for places that don't need to suffer, right? So that's the smart grid. The smart grid was put in place in a lot of places. In Boulder, Colorado, I think they started with a really super smart grid and didn't turn out so well because they found out they can't dig wires into rock. So there's a lot of failures of the smart grid around the country, but a lot of it has been adopted since I think the early 2000s. They've adopted a lot of these similar techniques. PG&E has a lot of issues with their grid, and I think that's where you see a lot of fires that happen, and some of the things where they try to isolate their grid, so they still have to build up their infrastructure. So when I talk about the impact of hemp, it's going to happen where you're going to see the more advanced grids will have the ability to bring back the energy. The less advanced grids will not. New England, like Con Ed, I don't trust them as much. Some of the I trust Texas has a really good grid system, and some of the California does not. So you'll see that kind of islanding, and you'll see that disparity.
Do you know, is there any sort of resiliency software simulation that's going into place? Because it seems like, obviously you don't want to do a live test necessarily, but it seems like if you can model the system, that you could do resiliency tests and say, okay, let's say we've got a transformer that's made somewhere out of the country and we don't have that transformer anymore. How do we reroute power to make the rest of the grid work? Is that sort of thing
so in the deck, if you look at some of the references I have there, most of all the reports from the cybersecurity reports and the cyber and security intelligence reports, even the EPI report, they have lots of models and simulations. There's also a link to the GitHub of the hemp from the EMP Commission, and all of the simulations that they perform is basically that. How do you switch out equipment? How do you test out equipment? What are the areas that will most likely be affected if you had different types of equipment installed? So check out that GitHub.
What of perhaps maybe the makers already provided for that? What of if one is wearing a pacemaker? Does that mean one always needs to wear aluminum shirt every time or so? If
you're what? I didn't hear that first part.
If you have a pacemaker.
Yeah. Pacemaker.
A pacemaker.
Yeah.
So does one have to wear aluminum shirt all the time also to protect against storage?
So the aluminum shirt, again, that's only going to protect you for so much. You're not gonna be protected by everything, right? And if you're afraid of a pacemaker stopping, yeah, I guess you could wear some aluminum lined jacket or something, and that'll protect you from getting shocked by a taser or something like that. So if you want to protect yourself against a taser, you can wear an aluminum jacket. Again, the EMP thing, it's gonna depend. It's gonna really depend on where you are and how close you are to the most effective part of it. And if you have a pacemaker, you may be vulnerable. I actually haven't researched that. I'll look into that if you want, but I didn't research any type of pacemaker effects. That's an interesting concept. Maybe it would.
So how about the
this new power generators that they charge, and they have like big batteries. Are these things, once they're disconnected, do they need to be protected, or would they be resilient to an attack like this?
As long as they wouldn't hold a current, I would say they would be fine if they're like somewhat shielded. But yeah, the key thing is, like what Hector was saying, if the device holds a current, the current essentially becomes like a lightning rod, only except it's like an EMP rod, where it literally gets hit by the EMP and it overcharges the circuit.
Yeah, perfectly said. Yeah, I think the current, so a battery will stay open, right? So open current. You don't want to, you're not using it, so you're fine. As long as you don't have a battery, connected to something and actually being discharged. If you did, you may actually end up charging the battery depending on your charging circuit.
Yeah,
but that's what would happen most likely.
Well, how would that work for, I know NextEra has, there's kind of a city that basically runs on solar power, and they have these huge battery arrays and that sort of thing where it's, you
talking about like Babcock Ranch or whatever?
Yeah, Babcock Ranch, for example. I mean, it's a great trial of renewable energy. How would that hold up?
I'm not a spokesperson. I'm not a spokesperson of FPL right now, but I would say if I was just an onlooker, I would think that the way it's set up, it's just it's a solar field, but it's connected to the grid. It's not a solar field for the city itself. So it's kind of like a partnership for, just to kind of help and promote renewables. It's not really.
Like, yeah, I mean, it seems like if you have solar panels generating energy, so it's up in effect, and then you have large battery arrays with charging circuits. So that stuff seems like it'd be live.
So renewable again. So renewable is going to be very, very useful for black starting a grid, because renewables don't need renewables need very little energy to start, right? You just need a sun. You got the sun connected. The sun's giving you power. It's even if you're a blackout, the sun's still giving you power. You just got to flip the switch back on, unplug it, plug it back in, kind of thing. So it's kind of very similar to a battery, where a battery has energy and it's not connected. You connect it, you're good. What you want to make sure is that when you have a solar grid connected to a solar panel site connected to a grid, it's PV site connected to a grid. If you did have to endure an E1, E2 event, you might have some sort of surge protection that triggers. You might have had some surge arresters that blow up or something. You may have had a trip if you're lucky and nothing got broken. Inverters might have blown up if they couldn't handle the surge. So best case scenario, nothing broke, and you could turn it back on. A worst case scenario, something did break and you could go replace equipment. So they would send out crews, and sometimes a lot of the sites, they already have equipment there to be replaced. So they could just switch out, like with a point of interconnection to the grid. They could go to that equipment, that substation, they could switch out whatever they need to. They could switch out cap banks and switch out all kinds of transformers. And they'll just install it. It takes, it'll take a few hours, maybe even 12 hours to get it up and running completely, and then, switch it back on. So that's what we'll probably most likely see is a blackout. You'll have renewable energy not connected for a while. You'll have these renewable energy sites that say, hey, I'm good, I can still operate. They'll turn them back on, they'll flip the switch, and then you'll have energy again. And then it's a matter of how to route that energy to the people who need the power, and the people who can get the power without, making sure the infrastructure is still there to give it to them. So that's why the smart grid has really helped, at least in Florida, to kind of be resilient towards these attacks. Once there's actually, I've heard stories of places in the country where the system is so not well thought out, you could throw some shoes on a power line and like have a cascade event and cause like half the state to go dark, right?
Yes.
And it's because they created these single point of failures that have yet to be untied, and it costs money and it's very logistics heavy, and they just don't invest in it. So there's still places like that.
So do we do like architectural reviews of those grid systems? Like, because it seems like you could almost, an experienced person like you could probably say, oh, look, I can see you have single points of failure in your electrical grid system. You should re-architect. I mean, it seems like there's maybe not, but you know what I mean? It seems like you could identify that from wiring diagrams, right? I mean,
yeah, and it goes back to what happened. It goes back to what happened in PG&E, and Rod was mentioning the Melcraft. The
Melcraft, yeah, Metcalf.
The Melcraft substation. So the Melcraft substation, I think, was targeted, and a lot of these substations are targeted because of the architectural design. So you want to find those points of pressure and target those places. A lot of the, I know that a lot of the substations have been hacked into by Chinese actors, and they've been focused on those substations that are critical to the infrastructure. So you focus for those, and then those are kind of like the ones that, if you take that one down, it can't support the switching and the support of the system. So you take down these like critical pieces. Again, it's islanded off, so you'll have events where the regions are very small. So you need to basically go and find all the different points of failure for the different regions that you want to attack. That's a good part of it, and the bad part of it is, yeah, I guess it's just somebody not taking time to invest in the infrastructure and get rid of that failure.
Yeah, it seems like it would be a helpful review. Obviously, I mean, that means capital. All right, obviously, it takes a lot of capital to create redundancy in big electrical systems. That's a lot of investment to make that happen.
And I suggest looking at reading that book, Smart Grid The Grid by Greta Bakke. She discusses why the grid is the way it is, and the idea that along the line we switched electricity as a commodity that we're turning in the marketplace. Is no longer a monopoly type thing. So the people in charge of keeping up with the grid's upkeep, they're not incentivized to do that. The people in charge of generating power and selling power, they're incentivized to buy and make power and sell it, and they ignore the public goods, which is the actual wires that transmit it, and that creates kind of like less focus on the actual infrastructure, more focus on the commodity being traded. So that's where they make the money. They don't care about the infrastructure. They keep going. A lot of the infrastructure that we have in place, it gets blackouts occur mainly because of vegetation, like trees and branches breaking stuff. So there's a lot of money invested in just clearing out trees all the time. That's why people don't make money off of distributing power, is because you got to invest it in this stuff, and typically it's left off to the governments to enforce regulations that will make these single points of failures less often created. So that's mainly why the grid is today. I think those opportunities to improve it are there. A lot of the utilities have taken upon themselves to kind of be more resilient, especially the ones that are in the coastal areas, because those are the ones that are being attacked mainly by disaster, like hurricanes and earthquakes, and those are the ones that would have the most benefit. So the money that they're getting from the cities and the states goes towards that hardening of the infrastructure in that area.
Yeah, more of a focus on return on capital.
Yeah, the Midwest, not so much, right? The Midwest, they're not investing as much because they don't have that much disaster. Maybe they have some storms here and there, but it's usually what happens. Yeah, I'm already over the time limit. Any other questions?
Yeah, well, no, this has been wonderful. Any last question?
No.
I have one if nobody else does. Just have you seen the FBI building that's down in Miramar? Have you seen that building?
No.
Okay. I used to work near there, and I must say it's got it's kind of like a glass building that looks like it has a lot of that metal reflective sort of glass, in there.
Yeah.
And it's got a lot of kind of non-parallel surfaces. And I was just curious what your thoughts were on that. It kind of looks like it's designed to shed RF, or something. I just wonder what you thought of it.
Yeah, so that's interesting. So to shed RF, you don't want to make. You want to make something round, right? To like protect against it. If you want to like emit it, then yeah, you want jagged stuff. you want to become like an antenna and like send out all kinds of crazy signals all over the place. So
that kind
yeah,
of makes
that could
consistent with why it looks that way. I think it's got a lot of those.
Yeah,
kind of
maybe.
images. It's kind of interesting. Yeah.
Yeah. I don't know. It's probably more artistic. I think it's about that really crazy looking one. Isn't that the one that like the
right
sun kind of reflects down and
yeah,
burns
it's got
people?
a lot of non-parallel surface. It's not like a typical glass-looking office building. It's got a lot of funky angles.
That must suck for a lot of birds, I guess. Maybe that's you get a lot of.
Well,
No, yeah.
Thank you very much, Hector. Once again, thank you, Ray. Thank you, Sam. Thank you, Chris. You guys have contributed and done this talk amazing. This will be posted on the YouTube channel, and hopefully many people will see it for months to come. And then hopefully we'll get, again, I'm calling for PG&E, for the state of California, where we have a lot of people as well, and would like to hear what you think about these threats and vulnerabilities and how they're being addressed. And for all of you, thank you for coming, and we'll see you soon in another meeting.
Yes.
Thank you. Thank you for presenting.
Okay, let me just end it with, this is all outside of FPL. These are my personal opinions. Disclaimer, just in case it does get posted. Appreciate you guys.
Yes.
Bye.
Yeah, no, thank you very much, and we appreciate the effort. Thank you.
Yes.
Thank you guys.
Bye bye.